Hello, another piece of musical gear for repair. I got this Axiom Pro 49 on eBay quite cheap because it's not working. About a year ago I posted another video repairing Axiom 49. I will link that video below. In that video the keyboard showed a so-called blue screen of death. And as I explained in that video, this symptom can be because of many problems. So this keyboard also has blue screen of death, but the problem can happen to be the same or it can happen to be different. We don't know. It just means that the computer inside the keyboard isn't working, or at least it is not able to display anything on the screen. So all we see is the backlight of the LCD screen and nothing else is happening. Let's check it out. I connected the USB cable. There you go. Backlight is on, some buttons are lighted as well, and nothing else is happening. I want to check if it would work powered from a power adapter, not from USB. And by the way, the Axiom 49 I repaired before took 12 volt supply. At least the marking here was 12 volts. And this one takes 9. And I suspect this is not very important, because most probably inside there is a voltage regulator which drops this input voltage to 5 volts anyway. I don't have a 9 volt supply handy, but I found this suitable connector, so let's use this lab supply instead. I set the voltage to 9 volts and let's check if the positive is in the center. Very important. Yes. As I suspected, the same thing powered from the power supply, not USB. I removed all the screws holding the top cover, and these are on the perimeter of the keyboard, plus in some deep holes here. There are also 5 pairs of screws holding the keyboard to the bottom of the case, and we don't need to remove them. So now the cover can be lifted right off. And there you go. This keyboard looks quite different inside from that Axiom 49 I repaired before. Much nicer construction, very nice looking surface mount boards all over the place. This looks like an aftertouch sensor. The key scan board and the main board. All the connectors disconnected, just to have a closer look, except the power connector, which is not in the way of anything. And by the way, I believe we should be able to quickly check if the thing is alive or not, even with nothing connected like so, just by plugging in USB and powering this thing up. And it should show up, if it's alive, in the list of USB devices in the computer, which it does not right now. I checked. Let's see what I understand here so far. There are 2 voltage regulators, and this one is producing 3.3 volt rail for the microcontroller and something else perhaps from the 5 volt rail. And the 5 volt rail is derived either from USB directly or from the external power supply, in which case this regulator is producing 5 volt rail from the input 9 volts. And of course it is tempting to check the reset chip, because it is known to be a problem in many keyboards, Axiom keyboards or other M-Audio keyboards, and it certainly was the problem in the keyboard I repaired before. So I believe I found it. Here it is, and in particular the reason I believe it is the reset chip, because the designator is U7. So conventionally U is used for ICs or integrated circuits as opposed to simple diodes or transistors. Let's say a similar looking package is right next to it and the designator is D4, so it must be a diode, and this one must be a transistor because the designator is Q2. The marking on the chip is AC981, and I'm not sure which chip is it. I found some datasheet which might be a right one, might be not. And this datasheet is About Richtech Micro Power Voltage Detectors, RT9819. And it covers the whole line of such chips in different packages with different voltage thresholds, with different reset delays, and the reset can be either active low or active high. Unfortunately, they don't specify how an actual chip would be marked. They propose to contact a sales representative for this. Here I captured power up on the scope. Channel 1 is 3.3 volt rail, channel 2 is the reset. We have 1 volt per division vertically and 200 milliseconds per division horizontally. The trigger is at 1 volt on channel 1, rising edge. So it triggered when power went up, and we see that the reset was held low for about 2.5 divisions, which is about half a second, and then it went up, and at this point the microcontroller must have started running. So it is exactly how it is supposed to work, not a problem at all here. I removed the board to have a look, and there is nothing at all on the other side. Let's remove this sticker from the microcontroller. And it is an XP microcontroller, which is marked LPC2146FBD64. This is an ARM7 processor. Here is the pinout. Let's start checking. A jumper can be used here in the power switch connector, in this position to power from the power supply, or in this position to power from USB. I didn't have experience with ARM processors so far, so I browsed through this user manual for this family and learned a few interesting things. In particular, here in the flash memory section, I learned about the bootloader, which is built into the chip. It's always there, we cannot change it, and it is executed every time the chip is powered on or reset. It is supposed to detect existence of valid user code in flash memory and if so, execute it. Otherwise, it starts this in-system programming command handler, which allows us to talk to the chip through a serial port and execute commands like get chip ID, read memory, erase memory, write new firmware into memory and such. And this command handler can be forced even if the application code exists by pulling low this pin during the startup. And how the microcontroller decides if there is valid user code, this is based on the checksum of the first 32 bytes of the flash memory. This area is for the interrupt vectors, which are 32-bit words. There are 8 of them, and if they sum up to 0, then the first one, which is called the reset vector, is used, and it usually contains jump instruction to the entry point of the user code. But there might be a complication, because there is this mechanism called code read protection. There are several levels available, and if enabled, it prevents reading the memory, and some levels even prevent entering this in-system programming mode. So let's give it a try. I traced the serial port pins from the chip, and the transmit pin is connected to the MIDI out. Receive pin is connected to this optocoupler, which is connected to MIDI in. So I soldered 4 wires, transmit, receive, ground and 5 volts. 5 volts is attached to the USB power pin, and this jumper is installed here. And I hooked it up to this USB to serial adapter, which has 5 volt TTL level signals here, as opposed to plus minus 12 volt RS-232. And the chip is 3.3 volts, but it has 5 volt tolerant pins, so we should be good to go. Here we are. I connected this USB to serial adapter, and I'm going to use this very simple terminal program, which is written in Python, and it's a part of Python language library. After experimenting with a few alternatives, I found this one is the easiest to use in this case, so let's give it a try. Now we are supposed to send question mark, and as you can see, the bootloader response was synchronized, which means it detected the speed of serial communication using that question mark symbol. And now we are supposed to confirm that everything is good using the same word. We got OK, and now we are supposed to enter crystal frequency in kilohertz, which is 12,000 in our case. We got another OK, and we are good to go. Let's try J command, which is to get part ID, and we got it. First 0 means return code of the command. 0 means clean execution, no errors. Then we have K, which is bootloader version, and we got it. Again, first 0 is no errors, then 12.2, supposed to be a bootloader version. Now let's try reading memory. The command is R. with starting address. Let's start from 0 and let's read first 32 bytes. And here we are. So we can read memory. The first 0 again is no problems. Then we have our data in so-called UU encoded form, which is one of the standard ways to encode binary data so that the result is printable characters. And after that we got checksum, and we are supposed to acknowledge that it's good by sending OK. So now we can issue another command. Let's try reading the whole memory. And the size would be 262.144. As you can see, the result we are getting is in chunks. And each chunk is followed by the checksum, and we are supposed to reply OK if it's OK. And we are getting next chunk, and so forth. So we could potentially copy all those chunks, save them in one file, use a UU decode tool, which is standard tool, and get our binary data this way. But it will take us forever to do so without some useful utility to acknowledge all these chunks with OK every time, then glue everything together, decode and such. So let me see what tools are available for this purpose. I looked around and found a few utilities. Some of them are for Windows only, which means not for me. I need something for Linux, and I found one called MXLI, and the latest version 3.1 didn't work for me. It fails during the initial phase when it tries to auto-detect something and sends some commands to the chip. At some point doesn't like some response and fails. So I tried previous version 2.3 and it works with this chip just fine. Let's give it a go. This is the highest baud rate which works, so it will take a while. Alright, we have our firmware. Let's have a look inside. Looks like sensible data, not just all zeros or ones. Here I found the date, January 29th, 2009. So, what did we learn so far? We learned that the microcontroller is alive, and it seems to me that it does not reach the point of initializing the USB, so we don't see this whole thing as a USB device when connected to the computer. But we can talk to the microcontroller through this in-system programming serial interface. And have you noticed that I didn't need to pull down that pin P014 to force this in-system programming mode? This pin is here somewhere, and it's connected to this pull-up resistor, which means that the other side of the resistor is connected to the power rail, 3.3 volts. and I thought I will need to solder a little wire at this point and attach it to the ground, but I didn't have to. And that means, I believe, that the bootloader does not detect valid application code, so it goes straight into this ISP mode, so we don't have to force it. And this, in turn, I believe, means that the first 32 bytes in the flash memory were corrupted. Something was corrupted in that area somehow. Let's have a closer look at our interrupt vectors. Here I printed them out. And this processor is little endian, which means lowest bytes go first. So our first interrupt vector is E5 9F 4034. I found this instruction set reference. Let's have a look. Here is the structure of the 32-bit instructions, and the first 4 bits, the highest 4 bits, is the condition, and in our case we are looking at, I believe, this unconditional load command. So let's have a look at the conditions. In this case the condition should be this, unconditional, which means E. The first 4 bits should be E, which we do have. Remember, we have E5. So we have our unconditional load command starting with E5. As we discussed, E means this condition is always, and 5 is here, which is 101. And 0 here, I believe, means that the addressing mode is immediate offset, which means the offset is part of the command. And 1 here means that the offset is applied first, before executing the load, not after. And the destination register for this to be a jump needs to be the PC register, which is program counter, which is the same as register 15. So we should expect in these 4 bits to have an F. And let's see what we got. We have 4 here, not F. So something is wrong. I wrote a little script in Perl language to produce the sum of 8 interrupt vectors, and here it is. It prints out these interrupt vectors and the sum is not 0. So no wonder the processor goes straight into the in-system programming mode. Look what I found. This is a firmware updater for Mac OS, and in the Mac world these DMG files are containers or archives, in other words, and I managed to extract these 4 files from it. This file is tiny. This, according to the name, probably has nothing to do with firmware. This one is tiny as well, but this one, I suspect, has both the macOS executable and perhaps the firmware as well inside of it somewhere. So let's have a closer look. So let's look at the hex dump of this file. And here we are. We have disk image background PNG, some other messages, which probably means it is the macOS executable Axiom Pro 49 firmware updater. Wonderful. So I wonder, how do we find the firmware in it? And I really hope it's not encrypted or scrambled in any way, otherwise we are out of luck. I found some signs that we might be lucky. Some messages which look like they belong to the firmware. Yeah, look at this. USB OK, MIDI. Yeah, Axiom Pro. Oh, look at this. Axiom Pro, May 12th, some time, and 2011. Yes, it does look like part of firmware. So how do we extract it from this big file? So I wrote a little script to look for the firmware inside that file, and the method is to read the file byte by byte and always keep the last 32 bytes in memory. So we have this sliding window of 32 bytes. So we are going to slide this window across the file, looking for E5 in the third byte. And if there is E5 there, then we produce this checksum of the 8 interrupt vectors, and if it is 0, we report this location here and continue looking just in case there are several such locations. So let's give it a go. And look at this. We found exactly one location inside of this file. So now we need to cut out our firmware from this location, and we don't know if it is exactly 256 kilobytes or slightly shorter. I really hope it is in one chunk and not separately, like a bootloader is one chunk and the main application is another chunk somewhere else. In that case we are probably out of luck. So I'm assuming this is one chunk, and if it is shorter than 256 kilobytes, then padding it with some garbage shouldn't hurt anything, I suppose. There is no checksum of the whole firmware, so we should be fine if we just cut out 256 kilobytes exactly. So let's do this. And here is the magic spell. XXD is another utility for all sorts of dumps. So I gave it this offset, beginning of the code in the file. This is the size in bytes and this is the file name. And we pipe result into another XXD command which does the reverse, which means it produces binary from the dump. And it needs the same offset but with minus sign, and the result should be our firmware. And let's run our check. And sure enough, the result is 0, because this was the criteria to locate this piece in the first place. But look at this. Here we do have an F in this location, which really means that this is a jump command. This F is for the register 15, which is PC, program counter. And all of them, all vectors, are jump commands except this one, which is the reserved vector to make this whole thing to add up to 0. Imagine filling this vector with zeros, then producing the checksum, and then negating that and putting it here, so the total becomes 0. So let's try flashing this firmware into the chip, which is a bit risky. There is always a chance that I didn't quite understand something and will make things worse, if it's possible at all to make things worse. The thing didn't work anyway, and there is always such a chance with any repair, and I think I should be able to write back whatever I read from the chip. So let's give it a go. This should be the right magic spell. It's running. Alright, it's done. Let's see if it helped. No luck so far. It still does not show up as a USB device in the computer, and I tried putting the board back into the keyboard. Nothing on the display. So perhaps this guess about cutting out the firmware from the updater didn't work for some reason, or something else is wrong. Maybe this chip is not quite working. No idea so far. But what's different is that now I need to pull low this P014 pin to enter the ISP mode. So I had to solder this piece of wire to talk to the chip again. One more thing I discovered is that if I read from the chip what I just programmed, the result is slightly different. Here, this firmware is what we cut out from the updater, and this is what I read from the chip, and I converted both from binary format to human readable hex format and compared with this diff utility. And as you can see, the first 64 bytes are different, and I believe it has to do with the bootloader. I remember reading in user manual that while bootloader is active, it remaps this region, essentially substitutes these 64 bytes to have its own interrupt vectors and such. So this MXLI utility reads these substituted 64 bytes. I suspect there must be a way to read exactly what we wrote into the chip, but apparently this MXLI utility at least doesn't know how to do that properly. And I think these are exactly the interrupt vectors we've seen before. I remember this 4 instead of expected F for this command to be a jump, and I think we've seen this checksum before as well. So I think that whatever I read from the chip for the first time is not the right thing. We essentially lost this region of the first 64 bytes, but not a big loss really, because we know that it didn't pass the checksum test, and that's why the chip went straight into the ISP mode without pulling this pin P014 low. I fetched this old laptop with Windows XP on it to run the Flash Magic utility from NXP, and sure enough, this tool knows how to read the chip properly. The result was in the Intel hex format, which is another variety of hex formats, and after conversion it matched exactly the file which I used to program the chip. Check this out, unbelievable. I managed to find this forum where people are talking about reflashing firmware in M-Audio keyboards. And way down here somewhere, here it is, this user shared firmware for Axiom Pro 61 and 49. Let's click on it. Here is an archive. I downloaded it and it has 2 hex files in it. So you see, this is the Intel hex format. Let's give this one a go. So I converted this file into the binary format, and let's have a look at the hex dump. I found this date inside, May 12th, 2011. Let's flash this thing into the chip. Check it out. It's working. There you go. So, let's review my working setup. There are probably many ways. I used this FTDI USB to serial adapter. They are about $5 on eBay from China. And I soldered 4 wires directly to the board. Here is the transmit from the board, so it is connected to the receive on the adapter, which is white. This is a receive to the board, so it's connected to the transmit from the adapter, which is green. And this black one is ground, which is connected to the ground here, which is black as well. And this point is 5 volts on the USB connector, which I connected to 5 volts on the adapter, which is also red. And here I used this little wire to pull the pin 014 low, and the pin is attached to this side of the resistor, and this is where I soldered my wire. And the other end, which is loose right now, I attached to this side of the capacitor, which is ground, but you can attach to any other point which is ground. And don't forget a jumper here to power this thing on, or alternatively you could solder this 5 volt wire after the jumper on this connector perhaps, or directly to the voltage regulator or something. But I found it convenient to be able to power it on and off here if necessary. And I used Flash Magic to program the chip. Let's review the settings. The chip is LPC2146. Then my USB to serial adapter happens to be COM4, and you can check it here in the device manager. Then the highest baud rate which worked for me was 38,400. The interface is non or ISP. The oscillator is 12 MHz. Then I checked here, erase blocks used by hex file. Here is my hex file. And I checked here, verify after programming, and fill unused flash. I'm not sure this one is important, but this is how it worked for me. So this video turned out to be more about ARM7 microcontroller programming techniques. I really hope someone will find it useful and interesting. I certainly learned a lot in the process. I will post a link to the forum in the description. It's better to use forum rather than YouTube comments if possible. If you liked the video, give it thumbs up. Consider subscribing to the channel. I have a lot of other projects waiting. Thank you for watching. Goodbye.